We'll start this presentation by looking at a real-world example of instability, and this is helicopter ground resonance. And this is an interaction between the aerodynamic forces created by the helicopter blades and the flow field and structure of the helicopter. Always respect the system's characteristic values. When will a bounded input produce an unbounded output? We'll answer this and several related questions in this presentation. We have introduced BIBO stability previously. It's a form of external stability. Remember, we had two different kinds of stability we discussed: internal stability, which is stability with respect to initial conditions, and external stability, which is stability with respect to the input. And we defined BIBO stability as every bounded input produces a bounded output. And when this definition says every, it means every. There is no bounded input which will cause the system to behave badly. We can rather easily come up with a simple mathematical condition for bounded input, bounded output stability. And the starting point for this is to look at the zero state response of a system. We'll develop this result here. So start by considering a system with an impulse response h of t, and also suppose that this h of t has no impulse in it, that is, m is less than n. The order of p of d is less than the order of q of d. We know that the output y of t is the convolution of the impulse response and the input, that is, the integral from minus infinity to infinity of h of tau, x of t minus tau, d tau. Now suppose our input x of t is bounded. That means that we can find a number k such that the absolute value of x of t is less than k for all t. We're now going to try to develop a bound for y of t, and we'll start from the convolution integral expression for y of t. That is, y of t is the integral from minus infinity to infinity of h of tau, x of t minus tau, d tau. We can take the absolute value of both sides, and then we can overbound the right-hand side by pulling the absolute value within inside the integral, and overbound that by then applying the absolute value to the individual terms. And that yields the result that the absolute value of y of t is less than or equal to the integral from minus infinity to infinity absolute value of h of tau times the absolute value of x of t minus tau d tau. Now, since we have a bound on the absolute value of x of t that works at each and every time, we can replace that into the expression. Then we find that the absolute value of y of t is less than or equal to the integral from minus infinity to infinity absolute value of h of tau times that bound k d tau. Now k can be pulled out of the integral, which gives us the absolute value of y of t is less than or equal to k times the integral from minus infinity to infinity of the absolute value of h of tau d tau. Consider this expression for a moment and ask yourself, under what condition can I find a bound on the absolute value of y of t? If the integral from minus infinity to infinity of the absolute value of h of tau d tau is a finite number, then this gives us a bound on the absolute value of y of t, and hence on y of t. So we have a bounded output if the integral from minus infinity to infinity of the absolute value of h of tau d tau is a finite number. Turns out the reverse is also true. Y of t will be bounded only if this integral is a finite number. So this condition that the integral be finite is an if and only if condition. That is, it's necessary and sufficient for bounded input, bounded output stability. Let's consider what this means in a graphical format. First, let's look at an impulse response. So here is an example impulse response. What does our integral condition say about the stability of the system with this response? Recall our condition. It says that the integral from minus infinity to infinity of the absolute value of h of tau d tau must be a finite number. Now the absolute value of h of t will look like this, and then that integral is the area underneath the curve. So if the area underneath the absolute value of the impulse response curve is finite, then the system will be bounded input, bounded output stable. Let's do a quick example. So let's consider this system y dot equals x. Is this BIBO stable? Well, our first step is to find the impulse response. So let's do that. We've got d times y of t equals x of t. So q of d is equal to d, and the order of q is 1. So n is 1. And p of d is 1. The order of p of d is 0. So m equals 0. Now m is less than n, and h of t then will contain no impulse at time 0. Now the characteristic values are the roots of q of d, and q of d is equal to d, so its root is lambda 1 equals 0. So there's only one mode, and that mode is c e to the 0t, since lambda is 0. So in other words, it's just c, a constant. Now we'll use the simplified impulse matching method we covered earlier. Since this is a first order system, we know yn at time 0 will be equal to 1, and therefore yn of t will be equal to 1, since we know that the mode must be a constant. Therefore, since yn of t is equal to 1 and p of d is equal to 1, then we know that h of t equals u of t. Now I've gone through this rather quickly, so you should go back and check to make sure you understand how I obtained h of t. In the upper left-hand corner is a graph of h of t, the unit step, and we recall the condition for BIBO stability. We had BIBO stability if and only if the integral from minus infinity to infinity of the absolute value of h of tau d tau was a finite number. Now if we find the area under the impulse response curve shown, we'll note that it's not finite. Therefore, we know that the system governed by the differential equation y dot equals x is BIBO unstable. That is, there is a bounded input which will make this output unbounded. This should not be surprising to you, because this is essentially the same system that we studied before, looking at the water bucket problem. We commented on how that was BIBO unstable, because we could put in a bounded input, which was a constant flow rate, and then the height of the water in the bucket would continuously rise, like a ramp. When will external BIBO stability be equivalent to internal stability? This is a question we'll tackle in detail in another presentation. For now, let's just give a brief overview. The answer is, if the external and internal system descriptions are equivalent, then external stability and internal stability will be equivalent. This requires that the system have no hidden modes, ones that are not affected by the input or are not affecting the output. Now, in most physical situations, this is true. We will examine some examples later where it is not.
Who are the Mythbusters? Andrew Savage.
I reject reality and substitute my own.
Ricky Heineman.
The thing that Andrew just doesn't understand about the situation is, it's not a democracy. It's a dictatorship.
Thomas Imahara. Elizabeth Byron.
I bet my firstborn he's not gonna curve.
And Kristen Chapman. With over 15 years of college experience.
I'm just many.
BIBO stands for bounded input, bounded output. The input is a unit step, which is a y value of 1 for infinity, as input to a system. If the resulting response signals do not have y values going to infinity, they are bounded output.
To show this as a block diagram, we draw a black box, which represents the system, except our black box is silver. We will draw the input as an arrow going into the black box, and the output coming out. Our input for this myth is a sleeve of Mentos, and we're trying to make it unbounded output.
And this is our black box.
We will put Mentos, our input, into a Diet Coke, our system, and see if we can achieve an unbounded output.
Ricky, what are you doing? I'm warming the soda up to above 98 degrees because currently I have a temperature. So I'm the best person to warm this up so that it will react better with Mentos. So I'm going to pull the soda bottle out of my jacket, hopefully above 72 degrees Fahrenheit. I'm going to put it on the ground, open it up. He's going to pop 3 Mentos in, and then we're going to run and hope we don't get caught. Ready? So we count. 3, 2, 1. Be prepared to back up.
That was not infinitely high.
No, Dad!
Last one kind of worked, but we really want to make this system go to infinity. So I'm warming up the second Coke in my jacket, and we're going to put an entire thing of Mentos in.
The high-speed shows with increased input, we still get a bounded output. Therefore, this system is BIBO stable and this myth is busted.
Oh, bloopers.
About
2 bloopers. Not this blooper. The loud, vindictive girl is finally... What is she doing?
She's slinking away.
I hate you all!
Do yourself a favor.
Don't try this at home.